Welcome to Lecture 3.6, Minors and Cofactors. We'll start with a simple but useful lemma. If A is a matrix with columns C1 up to Cn, and we construct a new matrix by adding the ith column to the jth column, for I different than j, or any scalar of the ith column to the jth column, then the determinant is unchanged. By the previous lecture, we know that the same result is going to hold for rows instead of columns. And when we row reduce matrices, that's what we're doing. We're subtracting some multiple of some column from another column to zero out some entries. So this process does not change the determinant. So keep that in mind. We will use it soon. Let's define the terms that appear in the title of this lecture. If A is an n by n matrix, which we will assume throughout, then we will define Aij to be the n minus 1 by n minus 1 matrix formed by removing the ith row and the jth column. Now the I minus j minor of A is just the determinant of that submatrix. So let me draw a picture of this. These are things I know you've seen. If you've ever computed a determinant before, you've done things like, well, so you have A11, A12, A13. You've done things like take this times the determinant of that minor, and that is A11. And then minus A12 times the determinant of the minor that you get by crossing these two out. So you take all of the other entries, and that's, I don't know how to write this, that's A12. And then you go plus, minus, and so forth. So that's, let me draw one more picture. So Aij is what you get by crossing out the ith row and the jth column and take all of the remaining entries. Those form an n by 1 by n by 1 minor matrix. So that's Aij. Now, it's common to call the matrix the minor. Technically, the minor is the actual determinant. We'll call Aij a submatrix sometimes. And the cofactor is just the minor up to sign. So it's either plus or minus 1 times the minor, depending on which row and which column we're at. So it's the minor times negative 1 to the I plus j. And the reason for that is, if you remember when you were taking determinants, we typically work across the top row, but you could do across the top or the first column, or you could do a different row or different column. And if there's a lot of zeros in a certain row or column, you may want to pick that row or column. And what you have to keep track of is, so if you work on the top row, you do minus, plus, minus, plus, minus, plus, minus. Sorry, I said it. So it looks like this. And if you work around, or if you work down or across a different row or column, then you have to follow this checkerboard. So if you work down the second column, you go minus, plus, minus, plus. So minus this entry, A12, times the minor, plus A1, so plus A22 times the corresponding minor. So typically how you've been taught is the determinant is like A11 times the minor Mij minus A12 times the minor, sorry, this should be 1 times the minor 12 plus A13 times the minor 13 minus A14 times the minor M14. And really, as far as I can tell, the only reason for the definition of cofactor is just to get rid of these minus signs. It's just easier to write it as A11 C11 plus A12 C12, and don't even worry about it. So build that negative sign into the definition, because when we have proofs and formulas, having this thing around here, or you don't even need either of these things. You get by with det of Aij, but having this around or this thing around is more clunky. It's easier to just call it Mij or Cij. Obviously, we are working toward the Laplace expansion formula that I outlined a few moments ago, and here's the first step. If A is an n by n matrix and the first column is E1, in other words, if in block form A is comprised of a 1 in the upper left entry, a column vector of n minus 1 zeros, a submatrix of size n minus 1 by n minus 1, and I don't care what these entries are, then the determinant of A is just the cofactor C11. In this case, that's equal to the determinant of this submatrix, because 1 plus 1 is even. Okay, so let's prove that. First thing to do is to use lemma 3.10, and it says we can take this first column and we can multiply it by suitable scalars and zero out all of these entries up here. So we can subtract suitable scalars of this column from the other columns and get zeros here. And so now we have reduced the problem to showing that the determinant of this matrix, this block diagonal matrix, is C11. Okay, so how do we do that? Let's define a function. So f is going to be from the set of all n minus 1 by n minus 1 matrices to whatever field we're over. And it's going to be defined as f of m equals the determinant of 1 m 0 0, also in block form. This is a number, this is a column vector of zeros, a row vector of zeros, and a submatrix. So what I'm going to claim is that f is actually the determinant function. So this is equal to the determinant of m, and that's exactly what we have to show. So remember, our goal is to show f of m equals the determinant of m, because that would show that this is equal to that. Okay, so what can we say about this function? So this function is clearly alternating, and it is also clearly n minus 1 linear form. And so it's clearly an n linear form. You could pull out, I think that's easy enough to see. Same if it's alternating. If you make two entries, or if you have two column vectors that are the same here, you're going to have two column vectors that are the same here, you get 0. So I'll let you check those if you don't believe me, but I think those are straightforward enough to state without proof. And also, the last thing is that f of the identity matrix, now this is the n minus 1 identity matrix. Let's check what that is. That is, notice what happens if you put the identity matrix here. You get the identity matrix, the n by n identity matrix. So that is, sorry, I should say that's the determinant of the n by n identity matrix, and that's equal to 1. So f is the unique alternating n minus 1 linear form that is equal to 1 on the identity matrix, and therefore it is the determinant function, and that's what we had to show. I think that's a neat proof. We don't really show all that much, and we use a lot of what we have built up. As a corollary of this, there's nothing special about writing the first column and E1. So we can replace the first column with the jth column and E1 with EI. And notice here that first and 1, these are equal. I and j don't have to be equal. So if your matrix looks like this, and you happen to have some column j where you have zeros everywhere except for a single 1, doesn't really matter where that 1 is. It can be in the jth row, or it can be in the ith, any other row. You can still take this submatrix Aij. I don't know how well I've drawn. Aij is the matrix that extends into everything other than these, and then you take the determinant of that, and the only thing you got to be careful with is that if I plus j is odd, you have to multiply by -1, and that's why we've basically used the notation of cofactors, because we don't have this clunky -1 at the I plus j sitting around if we do. So there's nothing really different about this than that. You just have to keep track. So use this result, and well, you can either prove it directly, but I think it's easier to use this result and make sure that you handle the signs appropriately. We now come to the Laplace expansion. So I've put the result of the last corollary right here for reference. And the Laplace expansion says that the determinant of A for any fixed j is the sum from I equals 1 to n of aij times the cofactor cij. So if you think about what this means, if you got the matrix A, and then you take the jth column, and the entries down here are going to be like A1j, A2j, down to Aij, down to Anj. Then you can just work your way down this column and multiply this entry times the corresponding cofactor, the determinant of what you get when you cross out this column and this row, up to plus or minus 1, of course, and then just do that all the way down the column. Now, we'll say that it's easy to show that if this holds, we could, there's nothing special about going down a column, we could go across a row. So we could instead take j equals 1 up to n and do aij, cij. Okay, so let's prove this. And to simplify things, I'm just going to take j equals 1. And I will let you verify as an exercise if you want for other j's. It's really no different. It just makes things slightly easier notationally. Okay, so let's suppose that A, let's write this in terms of its column vectors. I'll say it's equal to A1, A2, all the way up to AN, and these things are, so this is the first column. So the first column is going to be A11, A21, all the way up to AN1. And let's write so let's write A1 as a linear combination of E1 up to En. So A1 is A11 E1 plus A21 E2 plus all the way up to AN1 En. Okay, so let's compute the determinant. The determinant of A is the determinant. You can think of it as the determinant of the column vectors. So let's put this thing right here in the first column, sorry, first entry. A11 E1 plus all the way up to AN1 En, and then A2 all the way up to AN. And of course, we want to apply multilinearity to this. So we can break apart this first term into n sums, and for each one we can pull out the aij. So if we do that, we get A11 times the determinant of E1, A2, all the way up to AN, plus the second term is going to be A21 times the determinant of E2, A2, AN, all the way up to the last term, which is AN1 times the determinant of En, A2, AN. And now we just apply this result up here, the last corollary we saw. If in this case, if the ith column of A, so here we have a matrix. Each of these is a matrix. The ith column is, sorry, the first column is EI, then the determinant is C, in this case, I1. So this is going to be A11, C11. Now we have A21, C21, all the way up to AN1, CN1. And now the sum of these, if you add these up, you get exactly what we are looking for. And hopefully you can see why there's really nothing special about me using j equals 1 here. The same proof is going to hold. You just stick it in the ith entry, or the jth entry instead of the first entry. And I'll let you check that on your own time. Let's now apply what we've learned to systems of equations. Suppose we have an invertible matrix written as an n-tuple of its column vectors once again. So A is A1 up to AN. And remember that we can think of that as the image of the standard unit basis vectors E1 up to EN under A. We can write the system of equations AX equals U, where X is just a linear combination of the standard unit basis vectors, as follows. So this is the sum from j equals 1 up to n of xj times aj equals u. And for each k, we will define the matrix AK by just removing the kth column of A and plugging in u here. And let's compute the determinant, and we'll see something interesting. So before I do that, let me go back and unpack all of this, because I know it's hard with these sums and these indices to remember which is which. So once again, A you could think of as A1 up to AN, which really is AE1 up to AEN. Now this sum here, you can think of this as x1 up to xn is just x times 1, 0 up to plus all the way up to, this is x1, xn times en, so 0 up to 1. And that's where this comes from. This is just x1 e1 plus, I think I've said this before, but I find it so much psychologically easier to see some like this with dot dot dots instead of a sum. This for some reason is harder to unpack. And then finally, why is this the system AX equals U? I think it's clear why the right hand side is U. So what's the left hand side? Now one thing I want you to remember from, you probably remember this from your intro linear algebra days, is that if you have a matrix, let's put the columns A1, A2 up to AN, that one way to, and you want to multiply by x1 up to xn. One way, we often think that we multiply rows by columns, and that's how we usually do it when we compute it ourselves. But another very convenient way to multiply this is to do it by columns. So these are the columns, and so what we do is we multiply x1 times a1 plus x. I guess I don't have x2 times 8. So in other words, this is equal to x1 times, and I'm going to put hats here so you recognize your columns, x1 times a1 plus x2 times a2 plus all the way up to xn times an. So this is literally just a linear combination of the columns by these entries here. So that's exactly what this is saying right here. This is equal to AX, and this is equal, so AX equals U is this thing right here. Okay, now let's compute its determinant. So we're going to stick this thing here right in for U, and the determinant of AK is just the determinant of A1 up to AK minus 1. Now let's put x1 a1 plus xn an ak plus 1 all the way up to an. Of course, we want to break this up using multilinearity, and one thing to notice is that for all of these terms, except for the kth one, we're going to have a repeat. So we're going to have n terms, but we have an a1 here and an a1 here, an a2 and an a2, all the way up to an an and an an. The only one that's going to survive, remember this is an alternating form. If we have two entries that are the same, we get 0. So the only one that's going to survive is the kth one. So we will get out we can pull out the constant xk, the scalar, and times the determinant of a1 all the way up to ak minus 1, ak plus 1 all the way up to an. Okay. So now look what we have here. We have, so this thing here is just a. So we conclude that the determinant of ak equals xk times the determinant of a. Or what's more useful, maybe, perhaps, is that xk is the determinant of ak divided by the determinant of a. And I say, why is that more useful? Because we have a system of equations here. And we want to solve it typically. The the AIs or the AJs are the unknowns. And here's a formula for xk. So we literally have a formula for this solution of a system of equations involving determinants. Now we would still, this AK, is this matrix where you stick a U in here. We would still like to express this in terms of minors or cofactors, because I don't know, because that's something that we typically do by hand. So let's try that. So what we're going to do is we will apply Laplace expansion to this matrix AK. Okay, now where do I want to draw this? Let's do this. So AK, we have it right here. I'm going to write it in more matrix form. So this is A1, A2, and then in the, in the kth column, we have so we have U1, U2, all the way up to UN. And so this is in the kth column, and then we have all the way up to AN. So remember that these are all columns. So that's AK, and let's apply the Laplace expansion by going down the kth column. So let's write that over here. By Laplace expansion, determinant of AK is the sum. So we're going to go from I equals 1 up to n. So we're going to go down this way. And let's be careful as to what this is. So, so the ij entry is the ith row and the jth column. So all of these are going to have, so let's write that as, so I guess we'll have ui is the entry. And then by the Laplace expansion, we get the cofactor c, is it going to be CIK or CKI? I think it's going to be CIK, because again, the I means I steps down, and then K means K steps over. So K steps over every time. And so that is the determinant of AK. So now we can plug this back in here, and we get that XK is, how do I want to write this? Is, well, first we have a sum. So this is the determinant of A does not depend on the sum. So we can write this as 1 divided by the determinant of A. And now we can write this as the sum from I equals 1 up to n ui times CIK. So this is literally a formula for the solution of a system of equations involving the determinant and the cofactors, which are determinants, or plus or minus 1 determinants of the minors. So I should say this is wonderful. It's nice, but it's not very efficient. Computing determinants is a computationally expensive process. So it's not actually, it's not something you would ever program a computer to do. So you say, well, why are we doing it? it will come up. I think a formula like this is nice. It will come up in later proofs. So it's worth doing. It's worth seeing that it can be done, that these formulas do exist, even though there are much better ways to compute them. The result that we derived on the previous slide is called Cramer's rule. So here it is stated formally with that same formula for xk. And now we have a surprising corollary of Cramer's rule, which is the formula for the inverse of a matrix. So this explicitly tells you what the ij entry of the inverse is. It's the cofactor cji divided by determinant of a. Now remember that is -1 to the I plus j times the determinant of the submatrix AJI divided by the determinant of A. So in other words, the entries of the inverse are just given by determinants of the matrix and of submatrices. Now, because Cramer's rule is so computationally inefficient to compute solutions of systems, it's also very inefficient to compute the inverse of a matrix in this form as well. In other words, you should never do it. That said, I'm doing it because it's very close to what we have. It's not much further. And as I said before, it will come up in the proof of a result later in this class. Okay, so why is this the case? Well, it's actually not as hard as you might think. So if AX equals U, and A is invertible, then we can say that A inverse U equals X, right? We just take this and we multiply by A inverse on the left of both sides, and we get X. So let's first of all consider what this is. If I have, how do I want to put this in? So if I have a matrix, let's call this A inverse times U equals X. Now we always know what we have a formula for the kth entry. Say this is xk right here. It's just the dot product of this vector times the kth column. So this is the kth column. And so what is that kth column? So this is the well, we don't really have names for them. So let me set that the entries of here are, let me call them alphas, just because I don't want to call them aij's because that's the matrix A. So let's say that this is alpha k1, alpha k2, all the way up to alpha kn. And this, of course, is u1 up to un. So we know, just by computing matrices and vectors, that xk is alpha k1 u1 plus all the way up to alpha kn times un. Okay, so let's write this. So I'm going to write xk is the sum from I equals, or should I call it, let me do j equals 1 because that's the second entry. J equals 1 up to n of, now instead of using alpha, I'm going to write A inverse, and I'm going to use this notation for the kj entry times uj. Okay. Now by Cramer's rule, we also have a formula for this thing right here. Now let me change this I into a j to match the notation. So by Cramer's rule, this is, and I'm also going to stick the determinant in the inside of the sum. I think you'll see why momentarily. So this is equal to the sum from j equals 1 up to n times 1 divided by the determinant of A times cjk times uj. So by standard matrix multiplication, we have this equals x, so this times this, and by Cramer's rule, we have this. And look what we have. We have these two sums from 1 to n, and they both have a uj in it. In other words, this creature times uj has to be equal to this. And in other words, the kj entry of the inverse, it falls out at our lap. Here's a formula for it. The jk cofactor divided by the determinant of A. So the result here is just the same thing. Just instead of using j and k, I'm using I and k, because that's usually what we call an arbitrary entry. So just notice that the order jk and kj are reversed here. Okay, so that was probably easier than you expected. So that leads us to the end of this lecture. And I think what I will do next, it's a little bit out of place, not too much, are tensors. So previously I have stuck tensors at the very end of the class because I didn't really know where else to put them, and I think it's something that I needed at some point. But the tensor of two vector spaces is a way to multiply vector spaces together. That's not the direct product, and it involves bilinear functions. So it fits very nicely in this section of multilinearity. And I think it's better to see it earlier rather than later, because it is a fairly elementary concept, and you might be surprised of how it relates to things like multivariate polynomials and extending vector spaces over the real numbers to the complex numbers. So it's a neat topic. Hope you stick around. See you then.